Right, so gone live. Right, 5, 4, 3, 2, 1, go.
Hello, everyone. So, welcome to the Geological Society's virtual public lecture. I'm going to give a few seconds for people to join us, and then I'll start to introduce what we're going to cover today. So, our public lecture today is entitled When Mountains and Lake Move, Causes and Consequences, and it's going to be presented by John Reynolds. So throughout this lecture, your microphone is going to be muted and your video camera will be switched off, but you'll be able to hear and see the speakers and the slides. So my name is Alex Whitaker. I chair the Science Committee at the Geological Society of London. I'm on their council. And I'm also a senior lecturer at Imperial College London. So this lecture was originally scheduled in May 2020 to coincide with our year of life. But due to COVID restrictions and social distancing, we have postponed it until today. But we're going to explore today in this talk geological processes that occur on a weekly and seasonal basis in a young, dynamic mountain region such as the Himalaya or the Andes, and we will discover what communities in these regions deal with. So on top of seasonal events, there are less frequent but often far more catastrophic disasters associated with earthquakes and devastating floods from outbursts, for example, from glacial lakes, from landslide dams, and from intense rainstorms. And that, coupled with the impact of changing climate, means that we have a recipe for environments with very active geological and slope processes, and that can destroy the fabric of local society and, of course, influence the economic performance of these countries. So this talk describes how earthquakes, landslides, mountain collapses, glacial lake and landslide dam outburst floods, cloudbursts, and intense monsoon rains all contribute, often together, and impact communities and infrastructure in the Himalaya. So the talk is going to include forensic analysis of recent disasters to help communities and hydropower developers, and also governments better prepare and increase their resilience to both rapid geological processes and to climate change impacts. So Professor John Reynolds, who's giving the talk, so he's a leading world expert on glacial hazard assessment and remediation, and is also well known internationally through his textbook, An Introduction to Applied Environmental Geophysics. He is the managing director of Reynolds Limited. Now, at the end of John's presentation, there will be a 15-minute question and answer session. Please make sure that you submit your questions using the Q&A box function that you'll find on Zoom. Now, unfortunately, we may not be able to get through all of your questions. We'll do our best to answer them, but please feel free to post them, and I'll try and get through as many as I can. Finally, I want to say that this video will be live streamed and also recorded to YouTube, and we will be uploading this onto the Geological Society's channel. So I think that's enough from me by way of introduction. It is a real pleasure to invite John to start to introduce his talk. So John, I'm going to turn my camera off, and I invite you to turn on your microphone and camera and get going.
Thanks very much, Alex. I hope you can hear me and see the screen okay, and good evening, everyone. Thank you, Alex, for the introduction, and also to the Geological Society for the kind invitation to give this talk. I just wanted to kick off with the first slide, which you can see on the screen, which just gives an image of just how much the environment changes when a major earthquake strikes. And this is a situation in Nepal, a picture of a co-seismic rock avalanche in northern Nepal after the 2015 earthquakes. Now, what I want to be able to do in this presentation is to go through, just to give you a summary of the types of natural disasters, go through some relatively recent and one very recent situation in northern India, in Uttarakhand, the most recent one of which many of you may well have seen in the media. Then go on to just look very briefly at glacial lake outburst floods. And then the reason I put the next 4 items in blue is because it really follows. I'm going to focus on an area I've been doing a lot of field work in over the last few years in the Botokoshi Valley in northern central Nepal. And I want to go through and talk you through a whole sequence of disasters that have befallen one particular stretch of the valley from 2014 through to indeed 2020, and with prospects of many more to come in future years. And this is a major impact or risk to communities, hydropower, infrastructure, roads, and communication between China and Nepal, and economic development of Nepal as a country itself. So it's very significant. And then right at the end, I'll go on to look at something that's reasonably recently come to the fore, which is integrated geohazard assessments. And I'll explain a little bit more about what those are, and then wrap up with just a few very brief conclusions. So really what I wanted to be able to just summarize first of all is this range of different processes and timescales. So on the left-hand column, you can see I've put the timescales from millions of years going through ultimately through to sudden onset events and everything in between. The next 3 columns are all geological, geophysical, geotechnical, and geomorphic processes, which all cluster together in terms of geological processes. And then those on the right-hand 3 columns are all glaciological, climate change, meteorological, all to do with the hydrometeorological processes. But the reason I've put the arrows, the double-headed arrows at the bottom, is often what people tend to forget is the fact that there is a relationship between hydrological and meteorological processes and geological processes and vice versa. And the danger is when people tend to look at things in isolation, so an earthquake, a glacial lake outburst flood, a landslide, dam or what have you, and they're not seeing the entire set of processes. This is all part and parcel as one integrated mountain system, and we forget that at our cost. So to move on, and as we go through the talk, I'll be sort of coming back to this issue about relationship between geology and hydrology, hydrological and meteorological processes, as well as the different timescales, because we'll see how a lot of this, of the old geological or prehistoric, going back to on the geological time frame, preconditions landscapes that then have to interact with all the contemporary multitude of processes that are going on simultaneously. And this can have a major impact on how a particular environment is going to respond in a particular event. So to begin with, just having a quick look at the Uttarakhand area in northern India, and you can see down here where it's situated. So Uttarakhand is just west of Nepal in the northern part of India, just into the main Himal mountain areas. And I just want to concentrate in this area that's on the main screen here between Tibet and India. And we can see that in 2013, there was a 24-hour period, just 24 hours of intense cloudburst rainfall when between 300 millimeters and 450 millimeters of rain fell across this area. And you'll notice these river systems that I'm just, hopefully you can see my cursor across the screen, all drain and meet in the Alaknanda River and ultimately down into the Ganges and then further south this way. So when you start accumulating the flow from each of these tributaries, you can see how quickly the whole thing starts to cascade and build up. But just to begin with, I want to look at a couple of specific events. The first thing is I want to look at Kedarnath and go through and look at that particular event. And then briefly at the Vishnu Prayag hydropower station, which is one of the areas with the circles you see in blue with red around them, are those hydropower facilities, the dams most heavily damaged during the 2013 floods. And then we'll move briefly over to the February 2021 event that you might have seen in the media earlier this year. So to begin with, what we're seeing first of all is just, this is the town of Kedarnath on the right-hand side in the inset. And then just upstream of that, you have the Chobari Glacier, which you can see in more detail here. And what the local people had done is, because they're short of water in this challenging environment, they have built a masonry retaining wall along the right lateral moraine of this glacier in order to impound the water during the monsoon period to build up and collect this ephemeral seasonal amount of water that they could then access during the start of the dry season after the monsoon. And so they had artificially raised the level of Chobari Tal to the point where, coinciding with the response of the glacier to shrinkage because of climate change, this area of the right lateral moraine here reached a point where it could no longer sustain the water pressure from behind, and it just burst through during this peak cloudburst and joined with floods, surface floods emanating from the top of Chobari Glacier itself, then traveled downstream. They split into 3 tongues, which you can then see came down into, this is the situation before the event. So this is a 2011, a satellite image. And this is, you can see the catastrophe afterwards. You can see the effects from the northeast and from the northwest. And they combined in this area. This one actually went around the eastern side of Kedarnath and thankfully missed much of the town. But this actually impacted the northern half of the town itself. But in the area of, but the shrine itself was effectively intact. It survived the impact, and you can see from the photograph, you might just be able to see that here, the Hindu shrine survived, and it was the Hindus said that this was thanks to the Hindu gods protecting it. So moving on, let's just get rid of that. We can actually see then going across to the Vishnu Prayag hydropower station. And this is the event actually happening. You can see the deluge of water coming through, but it actually transported an entire year's worth of sediment flux from the catchment in just 4 days. And you can see it overwhelmed the headwork site that you can see on the left, and you can see the aftermath of the deposition on the right-hand side. And just to put it in context, this is about $1 billion worth of damage caused in a matter of a few hours, devastating for the region. And also the Kedarnath and the Uttarakhand disaster of 2013 resulted in 5,000 people being killed, and they are only able to recover 2,500 bodies, hugely impacting onto those communities and those families. But this is so typical of these catastrophic events. The scales can be absolutely immense. But going on to earlier this year in February, we can see that this is just a video screen capture from something that was published by India.com from citizen science. There were so many people out and about with their video cameras on their cameras, that they were phone cameras, that they could actually record what was going on. And you can see the scale of this debris-ridden, mud-ridden flood event coming through, hugely powerful. And this is and there were 2 hydropower stations, the Rishi Ganga hydropower station, which was totally destroyed, and then this one further downstream called the Tapovan hydropower project. And here you can see a picture prior to the event. It was still in construction at the time of the disaster in February, and this you can see afterwards. And this is an aerial photograph looking at what happened. But notice the deposits here are predominantly mud, not coarse debris. Whereas if you have a glacial outburst flood or some of these other floods you tend to get, like further up around in Uttarakhand and what have you, you can get an awful lot of debris. So something clearly happened that was different. So why are we not getting the coarse debris? We're getting this finer mud. Well, when we backtrack, and I did a forensic analysis of this event, partly for the World Bank, very quickly, the first few days after the event happened, and we very quickly were able to find out that despite all the media coverage, it's always a glacier burst, it's a glacial lake outburst flood, blah, de, blah, de, blah. It wasn't. It had nothing to do with any glacial lakes. There were none in the area. The nearest glacier terminated away from the impact area. What actually happened, well, there's a sequence. And again, coming back to this preconditioning notion, in 2016, these hanging glaciers collapsed and about 7 million cubic meters of ice fell down into this area and was then deposited along about 3.2 kilometers along the base of the valley. So that when this event, this landslide event happened in February, it was actually what is known as a stirstrom, because so much rock mass, somewhere between 10 and 25 million cubic meters of rock, fell and was pulverized on impact at the base here. And the frictional heating, coupled with the dust from the pulverized material, combined and melted this material, this remnants of the avalanche, to form added in about an extra 3 million cubic meters of water into the system, which was then energized by the dynamics of this flow coming downstream. And here we can see the residual remnant avalanche ice from 2016 covered with a patina of dust, typically from the air and wind that blows through these valleys. But you can see these little windows through this ice where the river is actually flowing underneath the whole time through here. And this ice was about 15 meters thick, up to 15 meters thick. And this is thought to have melted in order to contribute to this particular flood. So we know what happened downstream, but what still was not clear was what happened upstream. What really was the cause of this? Was it a one-off event? Well, as it happened, it's what we can see from this Chinese satellite image here, which we acquired from prior to the catastrophe in February. I've highlighted the structures that you can see, the geological structures, these very parallel and sub-parallel fractures across the area, cross-cut with other sets. You can see the jointing that's going on and this blockiness. And this is the area that was the source area in 2021, earlier this year, but this is the area of the hanging glacier that collapsed in 2016. And you can see all these other fractures all the way through this environment. It's a heavily jointed situation, preconditioned by geological processes going back through many, many millions of years. And so the combination of the ice avalanche happening in 2016, depositing the remnant ice along the valley, coupled then with the Sturstrom landslide that fell onto it, pulverized, heated it, and melted it, led to this catastrophe. And the sad thing about this, it's not a one-off. The chances are that with the conditions we're seeing there, it is likely to happen again, and not necessarily just once, but there could be other similar scale events going forwards. Well, let's move on quickly then to glacial hazards and looking at what happens here. Well, just take summarized in this cartoon, we have effectively with climate change, the glaciers have reached their maximum in the 1750s and 18th century. And then since then have retreated with climate change during deglaciation. And as the glaciers have retreated up valley, so lakes have formed in the upstream of the moraine dams. But you still get ice avalanches, you get slabs of ice collapsing, and so on and so forth. The front of the glaciers can collapse as part of an ice carving mechanism. I should point out this graphic suggests that there might even be sharks swimming around in these glacial lakes. That's not the case, clearly. But what this is supposed to represent is a displacement wave coming from an ice carving event that creates effectively a ripple effect that travels across the lake, and depending upon its size can either overtop or erode the moraine dam, leading to its breach, failure, and then the ensuing flood travels from tens to hundreds of kilometers downstream, ricocheting around meanders, reaching anything up to 50 meters above the height of the valley as it goes round the meanders. And therefore any infrastructure that happens to be in the way is just destroyed, communities wiped out. And that's, you don't stand a chance if you happen to be within the way. But the question then is, why do these lakes become mobilized? Well, I've mentioned the carving of the glaciers. They tend to be relatively small, but you can get large avalanches that collapse into these lakes. And it's those events that can cause a destabilization of the lake body itself. So we really have to try and understand how the different lake shapes, lake dimensions actually affect the way the lake body itself responds to the external stimuli. And so, for example, if you have a bowl-shaped lake, if you were to disturb that, like very much if you had a washing up bowl in the sink and you sloshed it around, it would just slop backwards and forwards, and you'd soon find out if it spilt over the rim. And that happens in lakes shaped like this, particularly from the input of a landslide. Then you can get a situation which is a smaller volume, typically less than 1% by volume of the lake, similar to throwing a pebble into a pond, where it's the wave energy that propagates along the lake itself. And these lakes could be 3 kilometers long, 100 meters deep. And the wave energy from the carving of the glacier then propagates maybe in no more than 30 centimeters high in the middle of the lake. But when it approaches the shore, because of the focusing of the wave energy into shallowing water, the wave builds. And so a 30 centimeter wave in the middle here can grow to a 2 meter high wave at the dam. And that can be enough to overtop and cause erosion and then lead to failure. But that's a displacement wave. The sage waves also you might recognize in videos. When there's an earthquake, you sometimes see swimming pools and the water is oscillating backwards and forwards. It's exactly the same process. But then the third case is when you get a large mass of debris collapsing into lake, typically by volume of the order of 5 to 10% of the lake volume. That physically displaces and pushes the water mass out of the way, a bit like a tsunami, and that then overtops or can overtop the moraine dam and destroying it. And then you've got an avalanche push wave event. But the critical thing about this is that depending upon how these waves slosh around, the burst that you get from a glacial lake can either be a single event or effectively a sequence of pulses of floods as these sage waves and these avalanche push waves slosh backwards and forwards like bath water in a tub. So let's have a look at the consequences. And here we can see a residual lake. This was a moraine. Here's the breach. This is one that formed in northern Nepal in 2002. And this is the deposit. Notice the coarseness of the debris that's deposited in this area. And you might just see down in this right-hand corner, these houses in this area. Thankfully, nobody was killed in this event. And this was caused by an ice avalanche. But to give you an idea of how they can impact onto hydropower, this is probably the wake-up call for Nepal in 1985, the Glacial event, when effectively 2 weeks before the inauguration by the Austrian finance minister, an avalanche fell into Glacial upstream. That created a wave that overtopped the moraine dam. And here comes the first wave. And notice in the previous image, I've arrowed this particular building. As the first wave comes through, notice it goes around it. But then afterwards, we notice that effectively, here's the same skyline as down in here. And that building is completely gone because this was taken out by a subsequent wave event. And this is very important because if you try to model the hydrographs coming from these events, if you think about calculating the amount of volume evacuated from a lake from comparing before and after an event, dividing that by saying it was one event, you get a totally misleading maximum peak discharge. And therefore the hydrographs are completely wrongly formulated in terms of modeling. So you really do have to understand the processes in order to see how these things go. But how big can these landslides be and these displacement waves be? Well, here's one we studied in 2002 at the Laguna Safuna and Cordillera Blanca in Peru. And here we have something like, roughly speaking, 10 million cubic meters of landslide that fell onto the glacier and then diverted into the lake. And that created displacement waves between 80, or avalanche push waves, I should say, between 80 and 110 meters high. I'll repeat that, 80 to 110 meters high. These are enormous. And this then sloshed backwards and forwards. Here you can actually see the scar of the avalanche push waves. It came over the top. It went over the top 4 times. Fortunately, the overspill was contained in this lower lake, and the only casualties were a herd of cattle that were grazing down in the foreground here. But then there were anything up to 14 oscillations of this wave, backwards and forwards, backwards and forwards, backwards and forwards. So they can have huge impact, and they can be huge in terms of scale, thankfully relatively rare. But now I want to go into an area in north central Nepal and just focus on this, the Botokoshi Valley, going from down through here in Kathmandu is to the southwest, just off to the left of the screen here. And then the Botokoshi goes up through here to this area when Nepal then turns into Tibet, and the international boundary is down through here. It's a sort of a protrusion of China into Nepal, or that's how the boundary goes. And so the northern part of this is all China, and this part to the south is all Nepal. And so for about 4 kilometers, this area has got a joint Sino-Nepalese boundary along the river. And I'll first want to look at the Juryland slide, then look at the processes in here, and then have a quick look at this, and then have a better look at the entire catchment, because I think there's some interesting lessons to be learned from all of this. So the Juryland slide happened in August 2014. Here we can actually see the landslide that occurred. It created a 40-meter high landslide dam. This formed a backwater impoundment reservoir 3 kilometers long, and it consumed and submerged an entire community in this area. And also the Sanima hydropower project powerhouse in this area was completely 2 stories high, submerged to beyond the roof line. The Sunkoshi hydropower project down here, this is the headwork site, and this was also damaged by debris coming from the avalanche. And then subsequent to this, there's been a long-standing attempt at trying to rebuild the road across here. And the other thing going across here that also had an impact was all the transmission lines for the upstream hydropower schemes were also destroyed. And so that meant nobody could transmit any electricity and therefore earn revenue since August 2014. But then we go on to 2015. So that was 2014 event. We now go into the earthquakes of 2015 in April and May. And this is typically what happened to many houses. Some collapsed completely, which you'll be familiar with in terms of the usual pictures of collapsed buildings and so on and so forth. This is one that is starting to tilt towards one side, and the back side of it is over basically the very steep slope of a valley. And you can see I'll put the vertical line here, and you can see how far that's deviated from the vertical. And the other side of it, you can see disappears down into the river valley. And so this is an area where you've got more rock slides, you've had destabilization of the slope, which has then collapsed into the river system, other collapsed buildings, very dynamic situation. And then going on a stage further, so we're used to buildings collapsing, we're used to the shaking from earthquakes, but in this particular case, we're also getting rock avalanches and what are called rock bombs. Notice this spherical boulder in here is about 2 meters, 1.5 to 2 meters diameter. And this has actually come through the roof, and you can see the hole it has made, and is basically become detached and bounced from the mountainside through the air so that its descent is effectively vertically onto the top of this house. And so it's come through the roof here, but it's also, this building has been affected by the lateral impact of rock avalanche coming from the side of the valley on top of the shaking. So if you were caught in this, you wouldn't stand a chance. So it's really dynamic, very powerful and lethal. But then the other situation is when we come to hydropower situations, we might think, well, okay, they're designed to withstand earthquakes. So here is one, the Upper Botokoshi hydropower project powerhouse. This is as it was built before the earthquakes. This is what's known as the penstock. This is what takes the water from upstream, is under high pressure because you've got 300-400 meters of head of water under high pressure. It feeds into the generators, it produces the electricity, which is then fed to the switchyard and then into the transmission lines and then taken downstream and exported south. And then the water that has come from the penstock goes into the tail race tunnel and rejoins the river to go on its merry way further south. But what happened in 2015, I should say, is that there were rock avalanches from up here. When the penstock pipe was being planned, they were humming and hawing, do we bury it to protect it from rockfall or do we not? The no protection, the exposed penstock was decided upon because it was marginally cheaper. In hindsight, huge mistake, because a boulder no bigger than about a meter in diameter actually collapsed onto the upper part of the penstock pipe, just further up here out of the screenshot, ruptured it, and the flood emanating from that then washed out all this material, and that then inundated the powerhouse with both water and debris and just meant that it could no longer function. So even though the powerhouse survived the earthquakes, it was destroyed just by this single boulder causing an impact onto the powerhouse penstock. And then we go into July 2016, and this is a picture of the Botokoshi headworks site. So the river flows down through here. The sluice gates block the flow when you're trying to collect the water to divert it. It goes into a desilting basin here, and hopefully the clean water then discharges down through twin pipes down through here to then join the penstock that we've just been seeing in the previous slide or two. And this is the retaining wall. And then every so often they open the sluice gates in here to then flush out the sediment back into the river so that you have an ecological resupply of fine sediment into the river system. That's what it looked like before a catastrophic multi-phase disaster in July 2016. This is what it looked like in July 2016 on the day after the event happened. You can see the river inundated the entire site. It actually blew out a 60-meter long segment of the retaining wall here, and here it is here, 50 meters across the side of the river. This was explosive, and it did so, and it must have been horrendous when it happened. It then released a separate deluge of water downstream with debris. And then the river was still in spate at this time because there'd been a heavy rainfall for the weeks beforehand. The rivers were all in spate. And the debris also blocked the sluice gates in this area, which exacerbated the event. And here you can see the boulders. These were 3, 4, 5 meters from top to toe, weighing about 150, 200, 400 tons, jammed into the radial gates, which meant they couldn't function. And that's what contributed to the diversion of the flow over the dam and into the desilting basin. And this is the consequence of that. But this is what happened, is that the desilting basin was able to take a certain amount of flow, but the river was so much in spate that it still eroded its way around around the right abutment of the headworks and breached through it about three days or so after the catastrophic flood. And the peak flood only took 15 to 20 minutes, but it was just exacerbating an already perilous situation. And the entire costs associated with that particular event amounted to, that's just a 15-20 minute event, cost $112 million or more in terms of rebuilding costs. So huge impact. So the the Botokoshi power station is located just at the corner here. So this is the border with China and Nepal. And I just want to start looking at the structures along this valley. And I want to draw your attention to these dashed areas that I've highlighted. These are individually what are called massive rock slope failures. This is where the whole mountainsides are collapsing over many, many years. And sometimes they speed up, sometimes they slow down. But in order to identify why is there a cluster of these events, it's because we can see what I've postulated here is a normal fault that comes through or perpendicular to the orientation of the main central thrust, which is orientated in this sort of direction. I've just indicated it here. And this structure is also parallel to the main central thrust. So this is an upper thrust, this is the main thrust, and there are some lower thrusts too, all of the same geometry, all dipping to the north-northeast, south-southwest, from the south-southwest. And so these events, these massive rock slope failures, are playing a huge role in how the environment behave subsequently. And let's go and have a look at some of these and see how it impacts on society. So I've looked at this area here. We're going to look in detail at some of these, but just briefly to help explain a little bit of the background of the event itself. A lot of people were saying, oh, it's these glacial lakes up here that burst, that contributed that deluge for 15 minutes downstream. Well, if we look at those in detail, there are two glacial lakes, one here, a tiny, tiny little lake, volume of only 130,000 cubic meters or so. This much larger lake in here, a superglacial lake in here, which has contributed to two major glacial outburst floods, one in 1981 and one in 1988. And the most lethal of those two events caused the death of over 200 Nepalis further downstream, because here we're in Tibet. So this event propagated, traveled all the way down the Poichu River into the Aran Valley, into the Botokoshi Valley, and then killed the residents, the Nepali residents in their communities further downstream. But what we found for this particular disaster is that, yes, there was a small contribution triggered in this event. And let's look at the next slide. Here is the little glacial lake. During the rainstorm, the general heavy rainstorm, a little mud flow was triggered into this area. That was enough because the lake was filled to capacity. It breached through the moraine. It then deposited the debris in this area, but not much further, just sand and a few fine grained sediments. But at this point, it was predominantly fine grained sediment and predominantly water. And when we come to so that drained down here, but it went down through a very steep area. And as it did, it caused valley flank collapses, which contributed more debris, which was then mobilized by the floods coming from a little bit from the Gloff, but mostly from the rivers in Spate, which were the couple of tributaries joining upstream of this point. That then entered the main Poichu here and traveled down. You can see the scar now is significantly wider. And as it propagated down here, it was then joined by other events from these side tributaries. Notice the scar width is getting wider as we go downstream. And at this particular point, there were a whole series of landslides. And it's thought that these landslides caused a short-term blockage in this area that was sufficient to actually impound about 2.5 million cubic meters of water in about 5 hours. And these landslide dams are notoriously short-lived. This one probably only of the order of 4 to 5 hours. And then it failed. And it was that event that actually contributed to this huge wavefront that transported huge amounts of coarse sediment. And although the flash flood itself only lasted for 15 to 20 minutes, the local people remember literally quaking in their houses as they could hear the sound of the boulders crashing into each other during night for 12 hours, a deafening sound that was even louder than the effects of the earthquakes in 2015. Must have been absolutely terrifying. They had no idea what they were going to wake up to, even if they were going to survive the night. So an absolutely terrifying event for the local people at that time. But then just looking at another aerial photograph, looking downstream this time at the at the Botokoshi, Upper Botokoshi headwork site. I just want to draw attention to these two areas of sediment. These are run-out routes for debris flows coming in from the right bank of the river. And the next photograph I'm going to show you, well, I'll come back to why this boulder is circled in a later slide, so just bear that as a placeholder. But this next slide is looking up in this area. So I was standing in this location looking up slope to see what was going on that slope. And this is what we could see. This is the back scarp of this massive rock slope failure. This is one of the areas which feeds the debris flows. And these terraces have actually been planted by farmers in order to grow maize. But these are all terraces formed at the tops of rotational failures. So if you can imagine a rotational failure, the top stays flat or flattish, and the farmers then were able to plant those in order to get some valuable food. But the tragedy of that is that in some monsoon of 2020, yet another debris flow came through here. And despite all the warnings of impending debris flows, landslides, and all the rest of it, locals just carried on as normal. And unfortunately, 11 people were killed. Again, tragic for those communities. But let's have another look at these massive rock slope failures. So the two run-out routes that I was alluding to are coming from here. This is where the dam is. This is where the people were killed in in the summer monsoon of 2020. But the whole of this area, you might see these lines. These are fractures, back scarps of areas where this material, you can see an upper one here, all of this is on the move away from this scarp here. And this is another massive rock slope failure in this area, which I'll come to in a moment. And so looking at the ground now and looking across the valley, these are the kinds of structures that we see. This is a panorama collated, as you can imagine, from a number of photographs. And I've just depicted, this is looking west. And here you can see these are main central thrust parallel structures dipping at the same angle, more or less, as the main central thrust towards the north. And we have some sub-parallel structures, and then these are intersected by conjugate structures going in the opposite direction, going east-west. And this is actually looking through the side of this north-south trending normal fault. So there's an awful lot going on structurally in this particular area. And we really do need to understand some of these structures. And so looking up the axis of the valley, so the Botokoshi is down in this valley here. This is looking towards Tibet. And you can see that the structures, the failure planes in this foreground are very much related to the structures you can see in the background. And these can be extended for kilometers, either side of the valley, predominantly on the west side of the valley. And these are thought to be conjugate structures, part of the debuttressing of this area following deglaciation and also erosion and down cutting by the river, but largely dominated by fault structures. And so I mentioned going on, so that was looking north into this area. We're now going to look a little bit into this area because this is a massive rock slope failure. And when the term is very descriptive, it is massive. The horizontal scale is about 2 kilometers from across the toe and almost 4 kilometers from toe to back scarp. And all of this is variably on the move. So I'm just going to look very briefly at this area in the yellow rectangle. And we can see here, this is the central part of the massive rock slope failure. These are the lateral scarps as the wedge failure starts to slip away from the back scarp, the lateral back scarp. And we can subdivide this area into multiple flow units. One here, one in the middle, one through here. These are the main ones. There are some subordinate ones as well, which I haven't picked out for the sake of some degree of clarity. We can see that a multitude of movement in this particular area. So after the earthquake of 2015, it was thought that this might have been a little bit destabilized, so that when you had this meteorological event in July 2016, this area became saturated. And with the scour of the river down at the bottom here in spate, it basically eroded the toe of this such that it started to mobilize this part of the slide. So a landslide happened in the August. So we had the catastrophic event in July. This landslide occurred in August 2016. And then because that started to mobilize the toe of this entire flow unit in the monsoon of 27, this started, and again in the monsoon of 2018, the upper part started to move. But I hasten to add, this lower part has been active all the way through, as has most of this in varying degrees. And I want to show you a picture of a house that's actually just behind where this arrow is located, because it is a lovely, well, it's a good example of what the locals are having to put up with. And it encapsulates it in a very graphic way of the plight of these local people. This house survived the 2015 earthquakes. Had it not, the residents would have been eligible for a $3,000 grant from the National Reconstruction Authority. But because it survived, and this damage was actually due to the landslide, the massive rock slope movement in August 2016, they could claim not a single cent. So they don't have any money to relocate. So they are forced with either becoming homeless and having to go to try and live off relatives in Kathmandu, or being mountain folk. They prefer to stay in the mountains. And so they're doing the best they can with a few bags of cement. Probably the family collected enough money just to buy a couple of bags of cement so they could patch up the area, put in new doors so they'd actually open. But look at the slope of this. Look at the angles of the courses of bricks. They're all over the place. This one's going up, this one's going down. This floor slab is split here. This is a different gradient to this one. The poor people here have got no option but to try and do the best they possibly can and survive as best they possibly can. But then looking just further up valley, we then look at the toe of this landslide. This is the one that happened in August 2016. There were two multi-story buildings. This one particularly destroyed. This was in June in 2017, beg pardon. And this is, again, largely uninhabitable, and it's on the move. The whole of this is on the move because the river is eroding the toe, and this area is saturated predominantly, especially during monsoon, and is on the move. And I'm just going to show you a sequence of photographs that take you through pre and post monsoon, going through a number of events. So this is going back into 2019. And here we can see those buildings. This lower one is largely gone now. It's tilted, it's sliding into the river. This one is tilting in different directions and falling apart. I'm just referring to this particular box culvert here by way of reference. There's also a road that goes across. Sorry, just move my cursor so you can see it. You might just see this line going across there. That's a road. This is the main export-import road from Tibet into Nepal and Nepal into Tibet. It is one of three major economic routes for export-import between Nepal and China. Hugely politically important, and the Chinese are putting a lot of money into this area. I won't go into the politics of it, I don't have time, but then we'll see as we go forward and just see, all right, you and I, perhaps we complain about the odd pothole, you know, opening up during the winter rains and the frosts, but just bear a thought for these people in this area. This is the original road level in 2017. This is what it was in May 2018. There's that box culvert. There's that house that was destroyed during the 2016 landslide. And this is the road coming up through here. All right, so it's dropped about 2 meters or so. In October the same year, it's dropped a further 10 meters in just a matter of a few months. And it's still on the go. And so if we now go back to over here, here's that box culvert again, just for point of reference. This is the main slide that's going through here, and this is also on the move. And there's still a potential as the river is eroding for this to collapse in a single event to cause a large scale landslide dam to block the river and impound millions of cubic meters of water that could then discharge. Here's looking back, and as we move on, sort of drawing towards the end of my presentation, you can see another perspective of this is the road in May 2018, and this is what it was like in October of the same year, more than 10 meters. You see the steep gradient down. This is still on the move, still on the move. And indeed, in the September of 2019, when I was able to revisit before the last visit there, before the COVID pandemic, the Chinese had built a concrete road. They had re-engineered the surface, built gabion wall structures to try and protect the toe of the slope. But notice the trees are still at an angle, and that's because this is still on the move. The whole of this road is being displaced towards the river, almost as an entity going this way. But that's not the end of it, because the other thing is there's surface runoff from here. And so if we look at the other way, going back the other way across exactly the same thing, this is again September 2019. And here we can see a river drainage, stream drainage, discharging across a little ford, trying to be culverted as best as possible to then go down into the river. But all that's happening is that this discharge is washing away the foundations from the road. It's undercutting it. They've now lost, in a matter of 3-4 months, about 2 to 3 meters of the road. There's the box culvert again, just for point of reference. And that water is going into the lower part of the slope. And that's just exacerbating the movement. And in the meantime, the rest of this is just running with water. There are surface springs. I noticed a couple of springs up here when I visited, even in September 2019. This is just on the move the whole time. And then if you're not sure about what evidence I have for this, let's have a look at the road where this red arrow is. Let's just have a look at that for a moment. This, when it was built in the March, April, May, probably April, May time, it was horizontal. This is September 2019. It's already dropped 0.5 meter, and it's already moved something like 0.6 of a meter towards the river. This is the lateral edge. This is the side of the boundary between the active central massive rock slope failure flow zone and the one adjacent to it, which is relatively static at the moment. But you can see how the concrete is just breaking up. It's just going nowhere. And as a consequence of that kind of damage, the chances are it will not survive the next couple of monsoons. And yet this is a major arterial route. So just to try and bring all this together, coming back to probably my first technical slide of saying you've got to look at the geology with the hydrogeology, hydrometeorology, because the two are very much related. And therefore, what we are seeing is very much there can be geological causes of disasters. Clearly, we know that, earthquakes, landslides, and they give rise to geological events, fair dues. Similarly, we can get monsoon floods, which cause hydrological events, fair dues, no surprises there. But then you can get hydrological causes of geological events. So you can get rain destabilizing hill slopes. That can lead to a landslide. So you have another geological process. That can form a landslide dam that then impounds water. And then you have another hydrological event, which is a cascaded, magnified event, many times the size of any individual constituent to that particular process. We call those multi-phase cascading disasters. And similarly, any combination of this, you have geological causes, hydrological causes, geological events, hydrological events, all of the above. And therefore, the disasters that you can get become more and more complicated and complex. But then coming back to what I was saying at the outset, we really do need to have a way of looking at this in an integrated way, at looking at the entire mountain system in an upstream catchment. What are the transboundary issues associated with that? Where are the hazards, say, for example, in Tibet? Where is the vulnerability down in Nepal? How do we manage that diplomatically and technically between the corresponding partner agencies? How do we facilitate that? How do we make sure that instead of just looking at water resource management, we're actually doing an integrated geohazard risk management that feeds into a disaster risk management of the entire catchment from headwaters in Tibet through to the Bay of Bengal downstream? Because what happens upstream will affect what's downstream. Indeed, there are historical records or prehistorical records in the geological record in the Bay of Bengal of thick piles of sediment identified from seismic records in the Bay of Bengal that have come from catastrophic major lake outbursts high in the Himalayas. And this river system that we're looking at here, the Arun Valley system, for example, is one. The Botokoshi is another. Both of these are sources of these massive catastrophic floods that can come through of, if dare I say it, sort of biblical proportions. These are once in a generation type events, well, hopefully no more than once in a generation. So these things have to be related in an integrated geohazard assessment. So just to conclude, therefore, I think I'm just about within my time, more or less. So we've got to appreciate that these natural disasters, rather than being an individual process type, an earthquake, glacial lake outburst, flood, landslide, have got to be, they're seen as constituents and components within a complex, related dynamic environment. And Alex in his introduction referred to the young mountains, you know, because the whole mountain building process in the Himalayas is still ongoing. India is still moving northwards into Tibet. The Himalayas are still rising. The rivers are still down cutting. That's part of a process that's been going on for millions of years. And that these natural processes that work on different timescales and different rates, yet all affect the subsequent behavior of a given site. This is the effect of we calling preconditioning. So what has happened before influences the behavior of a particular event and then subsequent to that. Fortunately, glacial lake outburst floods are much better understood than 20 years ago. And certainly when I started looking at these types of events more than 45 years ago. But the attribution and the linkage to climate change and the physical processes related to climate change, such as thawing permafrost, temperature rise, changes in soil moisture content, et cetera, increase in storminess, increasing occurrence of these cloudburst events and hugely intense monsoonal rains. That attribution and that linkage still remains annoyingly elusive. So there's plenty of work for young career geoscientists to get their teeth into if they should choose to do so. So therefore, the relationships between geological and hydrological processes are absolutely key to understanding how these catchments, these transboundary catchments particularly, might behave over time physically and in response to a changing environment. And this is why we're now advocating this integrated geohazard assessment of entire catchments. I'm looking at one, for example, in Tibet, which is 25,000 square kilometers, which then flows south into Nepal in the Arun Valley, and then down into India and forms part of the Brahmaputra tributary system down into Bangladesh and Bay of Bengal. But we're just looking at a transboundary integrated geohazard assessment disaster risk management project, setup project for 18 months in Nepal to look at how to develop the protocols for transnational issues, technical, diplomatic, political, so that these systems, these complex mountain systems can be better understood and better managed, more data sharing between reciprocal agencies. But this project, very much funded by, supported by the World Bank with support of the Japanese government, is due to start next month. And I'm fortunate to be appointed as a senior advisor to the World Bank to help steer that forward. And then hopefully that will then lead, if that is successful, it will lead into a $30 to $40 million 5-year project to actually implement the disaster risk management processes, a lot more research, a lot more field investigation. But the last thing I just want to leave you with a final thought. Given all of the societal hardships I've just mentioned going forward, the succession of 2014, 2015, 2016, 2017, etc., whole sequence of disasters befalling the same communities, these are now having to face with being overwhelmed by the COVID-19 pandemic. We heard on the media recently that India is running short of ventilators and oxygen. Nepal has run out. It doesn't have vaccines anymore. It doesn't have oxygen anymore. And people are walking for days to try and find a hotel bed, carrying their affected ill relations. And just bear that in mind. And if you see an opportunity to make a donation to one of the charities that's doing sterling work in places like Nepal, and others, not just in Nepal, but others across these areas, these hugely poor countries, please give a thought to helping out where you can. And I just leave you with one final thought. So thank you very much for staying with me during the last hour or 55 minutes or so. I just leave you with this picture, which just summarizes for me the kind of desolation and desperation of the locals with this lady sitting outside her house following a catastrophic monsoon torrent that in 15 minutes destroyed the river valley through the Chaku Valley, which feeds into the upper Botokoshi. And that was home to 3 hydropower facilities totaling about 40 megawatts. But this was the road that went up valley that brought traffic and therefore clients for whom she could then sell food and cook and provide produce and earn and eke out an existence. All of that is now gone. There's no road traffic at all, and it's unlikely that this will be rebuilt. So next time you think about complaining about our lot in the UK or wherever we're listening to this from, just bear a thought to the challenges posed to these people. Thank you.
Thanks very much, John, for a really thought-provoking talk on an incredibly important topic. Okay, we have questions and answers open, and people can type any questions that they have into the chat. Before we turn to questions, I must apologize for some of you who joined on Zoom, that there was a technical problem at the beginning, which meant that you missed the first 10 minutes of the talk. This talk is also being broadcast on YouTube, and we'll be uploading a recording onto our YouTube channel in due course. But on behalf of the Geological Society, I want to apologise for that. However, let's now move on to the questions. There are a number, some from our YouTube livecast and some from people here on the Zoom channel. I'm going to start with the first one that's posted from some of our viewers on YouTube. Are there satellites monitoring these areas regularly? And do you think that on top of the geotechnical factors, with global warming, will the kinds of events that you've been presenting, will they become more frequent?
Yes and yes is the short answer to both questions. I mean, most of us, I think, are increasingly familiar with Google Earth, and you can become an armchair global explorer with a glass of wine and going through looking at Google Earth. But in the same way, there are multitude of satellites. Virtually every nation seems to have its own plethora of satellites taking imagery on varying time frames and different resolutions. And there is a real wealth now of data gathering, not only in the optical regime, but also in the radar. You might be familiar with INSAR, using radar monitoring and the like. So yes, monitoring is not in real time, but this tends to be trying to get, I mean, Planet Labs produce images every day, but the satellites have to be tasked to take those over a specific site. And clearly there are only so many sites they can task them for. So to some extent, when we do a forensic analysis, we have to use those images that are most current, most appropriate, and in some cases have to pay a lot of money in order to acquire the satellite data to be able to do the studies. Geotechnically, yes, if you can focus on, like one of the landslides I was talking about, yes, you can focus in, you could put instrumentation, you could put boreholes, inclinometers, accelerometers, etc., etc. There are schemes now for doing using remote acoustic techniques to monitor the occurrence of events that occur well upstream, 30, 40 kilometers up, because they generate acoustic pulses like earthquake waves, the sound waves from the initial sound waves from earthquakes. And there are a multitude of different technologies now coming to the fore: infrasound, seismic networks, INSAR, and so on and so forth. So technology is playing a very, very important and growing role in this. With climate change, yes, we are seeing an increase in both frequency of events and magnitude of events. And this is what worries us hugely in terms of not only for the hydropower and infrastructure, but particularly also for the societies that are affected by these areas, because unfortunately they are really vulnerable. They are at the behest and the whim of the environment around them, and they can do nothing about it because they can't. We're fortunate in many cases that we can get up and move. They can't. They don't have the resources. They don't have the education. They don't. Everything is stacked against them, and therefore, what we're trying to do through this World Bank project is saying, and this is why I got involved with hydropower going back 20, 30 years ago, is if you want to take one sector that tends to be well funded, that has a cascade of benefits from energy production through to society, hydropower is probably one of the best in the high mountain environments. Because they have to improve roads, they have to put electrification in, they have to put schools in, they have to put health clinics in, et cetera, et cetera, et cetera. And therefore, there's this real cascade of benefits to society. And that was the motivation behind it. And we're seeing this, the pressure now, the urgency with which we need to get answers. Alex and I were talking about this before we went live, in terms of it's not an academic thing. You can sort of come to an answer in 5 years' time and all very nice, got a couple of papers out of it. Thank you very much. I get my promotion. Great. I'm trivializing academia, so forgive me. I used to work as an academic, so I've had a foot in both camps. But on the other hand, society is looking to the scientific community saying, we want answers, not in 5 years' time. We want an answer for the next monsoon. And that's really challenging because often the science isn't there to underpin it. So we're having to almost spend one season gathering the science and coming to some form of answer, a best guess at what's happening, in order to come up with our best guess solution to try and get them through the next monsoon. And then depending upon how the next monsoon goes, oh, that didn't quite work, let's change that. And it's not as if we have the opportunity of a 10-year period where we can test and try out different hypotheses and instruments and all the rest of it. It's measured in weeks to months, and that's a real challenge to get the science right and then get a solution that's right. So this is a huge area where lots and lots of opportunities for young career geoscientists, academic and in commerce. So that's a plea to the younger generation: STEM subjects at schools, good science degrees, good geology degrees at university, and get your science base, and then come and help.
Thanks very much. I'm going to take a question from Andrea, who's in the Zoom room. Are these events possible in the Alps as well? Or are they linked, for example, to a certain mountain mass, such as in the Himalaya or the Andes? Is the Himalaya special?
No, it isn't. It isn't. It's special because it's a fabulous place to go and visit, and culturally and all the rest of it. But geologically, it's, as I think I've demonstrated, it's geology in action. But these happen in any high mountain environment. The Rockies. You go to Alaska, go to Western Canada, go to Western US of A, etc. It's all the way, all the young mountain belts, it affects it. And coming back to the question in terms of the Alps, yes, indeed, at a different scale, because the mountains tend not to be quite so high, and therefore the magnitudes tend not to be as great. But then you've got much shorter distances between the events and the people, because you've got much denser communities populating the valley floors for much longer than you've had in say, Nepal or Bhutan. So yes, the vulnerability in places like the Alps is high because the population density is high. The hazard is not quite as high as in these young mountain environments, but when you take the scale of the hazard coupled with the scale of the vulnerability, the risk is still high. And some of the processes in terms of climate change, the feedback between the mountain systems and climate change is as valid in the Alps as it is anywhere else in high mountain environments.
Thanks very much. I'm going to take another question from our YouTube audience. And Ivana asked, haven't people lived with constant landsliding for centuries? So what did people do before? And have things gotten worse due to climate change or, for example, modern building practices?
Yeah, good questions. If you go to parts of the remote areas of Nepal, where, for example, the Sherpas have lived for centuries, and you go into some of the villages, you say, well, why have you not built in those areas? And they will come back and say, well, we know that's an avalanche run out route, so we don't build there. So they have developed over time their own empirical solution to dealing with their experience of avalanches. What's happening is the fact that the rate that they were able to adapt was sufficiently fast relative to the frequency of events in earlier times. But as pressure to develop and move into the mountain environments, populations have grown, more pressure to produce food, to farm, to cut forests down, and so on and so forth, has then meant there's a greater vulnerability now moving into these hazardous environments. And so what then we're seeing is there's an exacerbation because of the population, the growth in population density in these remote areas, coupled with inadequate housing guidelines. So, for example, in Nepal, just use that as an example, but you can apply this right the way across most mountain environments, including Turkey and the Alps and et cetera, is in some cases you have good building codes to withstand earthquakes and things like that sort, but in other cases they are still in development, and the governance and the jurisdiction and the policy within the government just isn't there to support it. And so any input you tend to get is very fragmented. It's only just starting to come together in Nepal. It's better developed in Pakistan, in India and Bhutan. They're better able to build the infrastructure to cope with it. But the other thing also, as I mentioned in my answer to one of the first questions, is that climate change is producing greater frequency of occurrence and greater magnitude when you get the extreme events. So we have to build that into our integrated geohazard assessments and our disaster risk management planning, so that we then are accounting for that growth in those areas. And it's no longer, I mean, we're starting to see it here in the UK, for example. We're seeing people are experiencing 2 1 in 100 year flood events just weeks apart. And they think, how does that work? That's only referring to the scale of event, not to the time frequency. And so what we are going to start seeing, and I'm seeing elsewhere, say, for example, in Pakistan, about 4 or 5 years ago, when I did a study in an area about 155 square kilometers, the upper Indus, we could see certain processes starting to happen, but would not really develop for 3 or 4 decades. We're now starting to see them already. So that's really accelerated the onset of some of these processes. And that's a wake-up call. I mean, when I first started doing hazard assessment, say, for example, in Peru in the mid-1980s, we were concentrating purely on the environments immediately around the glacial lakes, because that's what was impacting the lakes. With climate change, thawing permafrost, rising temperatures, we're now seeing an increase in high altitude rock avalanches becoming activated. That's particularly the case, including in Europe, in the Alps, over the last 15 years particularly. And that's only going to get worse.
Cool. Right, there's a couple more things here to answer that we could just wrap up. One is, are there any existing geological hazard maps, for example, landslides, rockfalls, in the border region between China and Nepal?
Yes and no. There are, in relation to, I mean, most countries now have seismic zoning maps. because the seismic zoning and seismic hazard assessment has been around for decades. It's well developed, and therefore that's the easy win. So yes, there are, but as soon as you start moving into to other areas, I mean, take for example glacial hazards. It's taken 15 years since I first started mooting it for the hydropower sector back in the early 1990s for that to become part of standard practice and government policy. And the issue about integrated geohazard assessment is only just starting to catch on. And I imagine that's going to take another 10 years plus before it becomes, you know, not just best practice, but established practice. But it needs to happen now, because people are no longer have the excuse that, oh, something might happen, we don't need to worry about it. The frequency is so low that at least it's not going to happen for the next 10 years. That isn't, you can't guarantee that. And I'll give you one last example because of time running out. I was speaking to somebody in southern Chile, in Patagonia, near a place called Valdivia. And she was asking me, oh, we don't need to worry about big earthquakes in this area because we had one 20 years ago. They're not due for another 20, 30 years. So we're not taking any precautions. A couple of weeks later, the area was hit by a 9.9 event. Boom. You just don't know. Nature throws up these surprises. We've got to be ready for nature to throw us the googly from left field, because it's constantly changing, it's constantly speeding up, it's constantly getting worse, and we need to catch up. And our research is lagging way behind.
Yeah. All right, I'm going to finish with one final question, which I think is quite pertinent. So an anonymous attendee has asked, where do we find out more about career opportunities in this field? So people are studying earth sciences or engineering, etc., at a university, and they want to go into this. What should they do?
I think there's a twofold response to that. I would like to see more university postgraduate courses being focused on this. I mean, with the energy transition and the climate emergencies, I mean, for example, in geology, the hydrocarbon sector is morphing towards more of the energy, renewable energy side. But there's a huge gap in the courses that are available in universities, particularly at postgraduate level, that allow people to go on and do an MSc in disaster risk management. You can, there are a few places where you can do that, and that's a good way. And then you can specialize in a particular, geotechnics or seismics or whatever. The other thing is also then go on to looking at PhDs if people are inclined to do that. But increasingly, because the hydropower sector in the Himalayas particularly is just going through the roof, it's a huge expansion, $250 billion worth of investment in the next 10 years. It's just an insane amount of money. Where are the people going to be to actually feed into that? Engineers, geotechnical engineers, seismologists, et cetera, the consulting engineers are going to need, multiple times the number of staff they have now, because people of my generation are getting to, close to retiring. Where's the next generation? We need to be bringing on the next generation. So, we're very keen to try and support universities. This is why the World Bank is working with this new Nepali natural disasters risk management authority in Nepal to build up a knowledge hub and a skills base in countries like in Nepal. But then hopefully there'll be opportunities for other people to come in and study with them, technology transfer, and vice versa. People from there to come back and share their information from the developing countries to work with university courses, consultancies like mine, for example, and others to try and get experience. It's still early days. And I would say, don't use the fact that it's early days. There aren't very many obvious opportunities out there to not go into it. Because I would say, get your qualifications, get your technical skills, and then you can search out those opportunities, because those opportunities are going to get on the jobs market very quickly.
Great, brilliant. All right. Well, I think it's 20 past 7 now, so we're over a lot of time. So I'm going to draw this to a close. But I want to thank John once more for a really inspiring talk that really gave us a lot to think about in terms of the challenges for tomorrow and how to make communities more resilient. So I think that this has been really great. So thanks very much. And I'd like to thank as well everyone who has joined us. And let me apologize once more for those of you who were affected by the technical difficulty at the beginning. I hope you join us again for more of our public lectures. So thank you very much.
Thank you everybody for attending.